When people say GPT-4 has hundreds of billions of parameters, or that Llama 3 comes in 8 billion and 70 billion parameter variants, what exactly do they mean? Parameters are the numerical values, specifically the weights and biases, that a neural network learns during training. They are the internal settings that determine how the model transforms any input into an output. Before training, these values are initialized randomly and convey no useful knowledge. After training on trillions of tokens of text, they collectively encode everything the model knows: grammar, facts, reasoning patterns, coding conventions, and the relationships between concepts across virtually every domain of human knowledge. Let us examine what parameters are, how they encode knowledge, and why the number of parameters in a model has such a profound effect on its capabilities and its costs. 5 key aspects of parameters explain what they are, how they scale, and the trade-offs involved in building and deploying large models. Every connection between neurons in a neural network is associated with a weight, a single floating point number that determines how strongly one neuron's output influences the next. A transformer layer in an LLM contains weight matrices for the attention mechanism, the query, key, value, and output projection matrices, and weight matrices for the feed-forward network that processes each token independently. During training, these weights are updated continuously via backpropagation to minimize prediction error. After training concludes, the weights are frozen and encode the patterns, facts, and reasoning capabilities the model has extracted from its training data. The entire intelligence of the model lives in these numbers. The relationship between parameter count and capability is not simply linear, but there is a consistent empirical pattern. Larger models, those with more parameters, generally perform better across a wide range of tasks. This is because more parameters provide more capacity to store knowledge and represent complex patterns. A 7 billion parameter model can hold a respectable knowledge base and perform competent reasoning. A 70 billion parameter model can handle more nuanced tasks and more complex multi-step reasoning. Models with hundreds of billions of parameters demonstrate sophisticated capabilities that smaller models cannot approach. This is why organizations competing at the frontier of AI capability invest so heavily in scale. Neural scaling laws, empirically established by researchers at OpenAI and DeepMind, describe remarkably predictable relationships between model performance and the number of parameters, the volume of training data, and the amount of compute used for training. The chinchilla scaling laws in particular establish that, for a given compute budget, it is more efficient to train a smaller model on more data than to train a larger model on less data. These laws allow AI researchers to predict, before spending millions on training, approximately how capable a model will be and to allocate their compute budget optimally between model size and training data volume. Parameter count is one of the primary determinants of the computational resources required to run an AI model. Each parameter in a model must be loaded into GPU memory during inference, and larger models require more powerful hardware. A 7 billion parameter model in 16-bit floating point precision requires approximately 14 gigabytes of GPU memory, manageable on a single consumer GPU. A 70 billion parameter model requires approximately 140 gigabytes, necessitating multiple high-end data center GPUs. Models with hundreds of billions of parameters require specialized infrastructure, making their deployment expensive. The memory requirement of parameters is therefore a key architectural constraint for AI system design. Quantization is a technique for reducing the memory footprint and inference cost of large models by representing their parameters with fewer bits of precision. A standard 32-bit floating point weight occupies 4 bytes of memory. Quantizing to 16-bit halves the memory requirement. Quantizing to 8-bit reduces it by 75%. Quantizing to 4-bit reduces it by 87.5%. Modern quantization techniques, including GPTQ, AWQ, and Llama.cpp's GDUF format, achieve this compression with surprisingly small losses in model capability, making it practical to run models with tens of billions of parameters on consumer hardware. Quantization is one of the key enabling technologies for local AI deployment. 4 essential terms for understanding how parameters define model scale, capability, and deployment efficiency. In a transformer-based LLM, the weight matrices are the dominant type of parameter. The attention mechanism requires 4 weight matrices per attention head per layer: the query projection, the key projection, the value projection, and the output projection. The feed-forward network requires 2 weight matrices per layer. For a model with 96 layers and 96 attention heads, this amounts to hundreds of millions of individual weight values per layer, summing to tens or hundreds of billions across the full model. Each weight is a single floating point number, but its value has been precisely tuned through trillions of gradient updates to contribute to the model's overall capability. The bias term is a smaller but important component of the parameter count. While weights scale quadratically with layer width, because they represent connections between neurons, biases scale linearly, since each neuron has exactly one bias regardless of the number of inputs. Biases allow each neuron to have a default activation level that can be shifted up or down regardless of what inputs it receives. Without biases, many neural network architectures would be unable to represent certain classes of functions. In practice, biases constitute a small fraction of total parameters, but contribute meaningfully to the model's flexibility and representational power. Model scale is reported in terms of the total number of trainable parameters, the weights and biases that are updated during training. Consumer-grade open-source models like Llama 3.2 are available in 1 billion, 3 billion, and 8 billion parameter versions, suitable for deployment on phones and laptops. Research-grade open models like Llama 3.1405b offer frontier-level capabilities requiring data center infrastructure. Proprietary frontier models, like GPT-4, are believed to have hundreds of billions of parameters. Model cards, standardized documentation sheets published by model developers, typically report parameter counts alongside training data descriptions, evaluation results, and intended use guidelines. Quantization works by mapping the continuous range of floating point weight values to a smaller set of discrete values representable with fewer bits. The key challenge is doing this without significantly degrading model quality. Naive quantization can cause large errors for weights with unusual distributions, but modern post-training quantization techniques like GPTQ and AWQ use sophisticated calibration procedures to minimize these errors. The result is that a 4-bit quantized version of a 70 billion parameter model can run on a single consumer GPU with 48 gigabytes of VRAM, hardware that was unaffordable to most individuals just a few years ago, making frontier-scale AI capabilities genuinely democratically accessible. Let us now examine how parameter scale translates to real-world deployment decisions and the emerging techniques that make large models more accessible and efficient. For practical considerations around parameter scale shape how organizations choose, deploy, and fine-tune AI models for real-world applications. One of the most practically important properties of larger models is their superior few-shot generalization, their ability to perform new tasks accurately when given only a handful of examples in the prompt. Smaller models typically require extensive fine-tuning on task-specific datasets to perform well. Larger models can often adapt to new tasks through in-context learning alone, simply by seeing a few examples of the desired input-output format. This capability dramatically reduces the data and engineering resources required to deploy AI across diverse use cases and makes larger models far more versatile tools for organizations with varied and evolving AI needs. Despite the capability advantages of large models, there are many applications where smaller models, those with 1 to 7 billion parameters, are preferable or necessary. Edge deployment on smartphones, IoT devices, and embedded systems requires models that fit within extremely tight memory and compute budgets. Applications with strict latency requirements, such as real-time speech recognition or on-device text completion, benefit from the faster inference speed of smaller models. And applications with data privacy requirements, where user data cannot leave the device, demand local inference with models small enough to run without cloud infrastructure. Fine-tuning a model with billions of parameters on task-specific data requires enormous compute resources. Updating all parameters is expensive. Low-rank adaptation, or LoRa, addresses this by adding small trainable matrices to specific layers of the frozen pre-trained model and training only these new matrices, which typically represent less than 1% of the total parameter count. The result is a fine-tuned model that performs comparably to full fine-tuning while requiring orders of magnitude less GPU memory and training time. LoRa adapters can be saved separately from the base model and swapped in and out dynamically, enabling efficient multitask deployment of a single base model. Model cards are standardized documentation sheets that responsible AI developers publish alongside their models. A well-constructed model card includes the parameter count, the architecture type, the training data description and size, the training compute used, performance benchmarks across standard evaluation suites, known limitations and biases, recommended use cases, and guidance on how not to use the model. The EU AI Act and other regulatory frameworks are increasingly requiring model documentation of this kind for high-risk AI systems. For practitioners evaluating models for enterprise deployment, the model card is the first document to consult when assessing whether a model's scale, capabilities, and limitations are appropriate for the intended application. Let us bring together the essential points from our exploration of parameters in AI models. To explore more key concepts in generative AI, check the link in the description. If you found this helpful, please like and subscribe. Thank you for watching. If you found this helpful, please like and subscribe. See you in the next video.